In this video, we are going to look at more problems, more examples where we are going to find intervals of concavity. We will start off with a simpler example, and then we'll look at some things that are a little bit trickier. Right, so here we have a polynomial, h of x equals negative x cubed plus 6x squared minus 9x minus 1. To find those intervals of concavity, we'll first observe this function is defined everywhere, so there are no places where it's undefined. If we take our first derivative, it's going to be negative 3x squared plus 12x minus 9. Take the second derivative. We have negative 6x plus 12. What are we going to do with that second derivative? Well, we're going to set it equal to 0. I'm going to scribble this out for a minute. We'll do those on a different page. So if we set this equal to 0, then negative 6x plus 12 is 0, and x is equal to 2. What are we going to now do with that? Well, we're going to do a sign chart, trying to say something about concavity, so that's looking at a sign chart for the second derivative. We will go from negative infinity up to 2, and then we'll go from 2 to infinity. We need to plug in some value between negative infinity and 2, so like 0. We are plugging that into the second derivative. Plug that into the second derivative here. If you plug in 0, you'll get positive 12. All I care about is the sign on that, so we get positive. If we plug in something larger than 2, so like 10, negative 6 times 10 is negative 60 plus 12 is some negative value. What negative value? Doesn't actually matter. You just need to observe that it's negative. And so, what is true? This function f is concave up on negative infinity to 2, and f is concave down on 2 to infinity. If we were to plug 2 into the original function, 2 comma h of 2, which is 2 comma, we would get negative 3 as an output. If we plug in 2, this is an inflection point. Great. And the only thing here, I should have called that the second derivative. This is of h. And this should have been an h as well. Our original function was a function h. This should have been h as well. Goodness, right? So this was h of x. Excellent. All right, let's look at the second example. So in this second example, we're going to ignore the first one here. We'll ignore the third one for a minute. We want to find f of x. We want to find out where's this concave up and down again. Is there anywhere that this function is undefined? Well, it would be undefined if this denominator was equal to 0. That will only happen if x is plus or minus the square root of negative 1/3. And so there's no real values. The square root of a negative is an imaginary value. So we won't have to worry about that point. What else do we need to do then? Well, now we need to also take our first derivative and then take our second derivative. So our first derivative, if you do the quotient rule there, low d high minus high d low square the bottom, and away we go. So if we take our derivative there, we will get 4x over 3x squared plus 1 squared. That is our first derivative after you clean it up and all that mess. From this first derivative, we are then going to take our second derivative. So here we will have quotient rule again, so low d high minus high d low Don't forget your chain rule when you're taking the derivative of the bottom piece. Square the bottom. It's already squared, but we're squaring that square, and away we go. And if you go through and do some of this cleanup, we have 4 times 3x squared plus 1 squared minus, let's see, 48 x squared times 3x squared plus 1 over 3x squared plus 1 cubed. You could, up here, factor out a 3x squared plus 1. You'll have 12x squared plus 4 minus that 48x squared. Oh, I got ahead of myself in that denominator up here. That should have been to the 4th power. One of those, that 3x squared plus 1 will cancel out with one of those, so that's why I got ahead of myself a little bit. And on the top, we will have something like negative 36x squared plus 4 over 3x squared plus 1 cubed. All right, so that is our second derivative. What are we going to do with it? Well, we're going to set it equal to 0. So we're setting that numerator equal to 0. That's going to be 0 if x squared is, let's see, I suppose 4 over 36. And if we have 4 over 36 there, we would then get 2 6 plus or minus 2/6. Actually, let me back that up. So then x squared is 1/9. So x is plus or minus 1/3. All right, so at plus and minus 1/3, those are potential changes in concavity. So we're going to do a sine chart for our second derivative, going from negative infinity up to negative 1/3. Go from negative 1/3 up to positive 1/3. And then from 1/3 to infinity. And if we were to plug something smaller than negative 1/3, so like negative 10, plug that in here, that denominator is always going to be positive, because when we square this and multiply by 3, that denominator is always going to be positive. We only need to think about what's going to happen in the numerator on this particular problem. Negative 10 squared is positive 100 times negative 36 is negative 3600. Negative 3600 plus 4 is some negative over a positive is negative. So we have a negative here. Plug in 0 and we will get a positive. Plug in something larger than 1/3 and we get a negative. So what does that tell us about our function? Well, f is concave down. It is concave down on the interval from negative infinity to negative 1/3, together with 1/3 to infinity, and it is concave up on the interval from negative 1/3 to positive 1/3. We will have inflection points at both negative 1/3 and positive 1/3. But since we were only asked about the concavity, we will look at that there. We will look at the third remaining example in our next video. I will see you there.